good morning. Thank you all for coming. This is quite a crowd, and it's not me. That's obviously a testament to how popular the Istio project is, how much interest everybody's got in it. So this is awesome to see. My name is Matt Turner. I tweet and have a website, as you might imagine. I'm a software engineer at Tetrate. We're a startup doing Istio and service mesh related stuff. We are, of course, hiring. That's all I'll say on that. And I'm here to talk to you about Istio, specifically the packet side view. So what that means is what we're going to try to learn today is how a packet traverses through an Istio system. And obviously that leans heavily on the Envoy proxy, as you probably know. And the exposition I'm going to give is Istio in a Kubernetes cluster, because that's by far the most common deployment scenario. And hopefully this is KubeCon. We should all know a little bit about Kubernetes already. So that's the easiest way to explain it as well. This isn't like an introduction to Istio. I'm not going to give you the pitch about Istio's features. There's a bunch of great material out there on that already. What I'm going to cover is how a packet goes kind of east to west through the system. We're going to see how Envoy gets involved, and we're going to see all of the control plane components involved as well on what they do. And what this will hopefully do is build you a useful mental model for sort of reasoning about Istio, for understanding the emergent behavior that you see from this whole service mesh, for understanding how it does what it does and why it does it that way. There are a couple of interesting architectural features that we'll cover, so if you ever find yourself having to defend Istio to a boss or somebody who says, oh, I don't like it, I don't think we should use it, hopefully this will help. And while Istio is an extremely mature and stable piece of software, if ever you should find a bug, in the rare event that you find a bug, hopefully this mental model will help with debugging as well. Just to get the most out of this talk, it would be useful if you knew a bit of basic networking knowledge, right? What's an IP address? What's a route table? A bit of Kubernetes knowledge. This is KubeCon, although I have talked to crowds when nobody's even heard of Kubernetes. But if you know what a deployment is, a service, the fact that there's an overlay network, that'll be useful. And as I say, this is a deep dive. We're going to look at how Istio works. So it would be great if you already knew kind of what it is and what it's trying to do. Because I don't have the time to cover that. 35 minutes isn't very long. I've had to cut a lot of the introductory slides. But hopefully everybody can keep up. So just to kick us off, this is your standard Istio diagram, right? Straight off istio.io. This is what we're aiming for. This is what we'll be explaining. So what we're looking at here is a service mesh, as you know, right? And ultimately what we've got is two services, service A trying to talk to service B. And the way, I'm sure you know that happens in Istio is through a proxy, specifically the Envoy proxy, which has just graduated into the CNCF. Congratulations to those guys. So we use what's called the Sidecar model of taking one of these Envoy HTTP proxies and strapping it alongside every service in that service's pod. Because we used to have monoliths, right? Service A and Service B used to be classes in a Java program, and Service A used to talk to Service B by doing a method call. Then this whole microservices thing happened, and they're now separate Unix processes in separate containers on separate machines. So that method call became a network call, and that can be slow and it can be unreliable. So for a very brief history, what we originally did, I guess, was add a library like Hystrix or Finigal to our code. Right, which would do things that you now need now you're making those network calls, which is retries and timeouts and all those kind of things. There were a few problems with that. We've suddenly taken this microservice and we've built, I'm going to call it a mini lith, right? We added a whole bunch of code back in, like a really big fat library that did all of this stuff. That probably had way more code in it than our business logic. And so every time that's got an upgrade or a CVE, we have to roll the whole thing. We have to be able to redeploy our service. So you better hope the test pass and it builds on master. And they just use a lot of memory. And they're, Hystrix and Finigal are JVM only. These libraries didn't exist for every language. So there were a few problems. So this has now come out of process. So, the Istio team looked around and saw the Envoy proxy is a really great HTTP proxy. It has all of these features we need. So what Istio does is strap it alongside. So I guess a service mesh, if you're being pedantic, is this mesh of services, service A and service B, with their proxies. What Istio adds, Istio is this control plane, these three Pilot, Mixer, and Citadel components that I'll go through. And what they do is they do magic, and they configure the proxy to do magic to give you the emergent behavior that you want. Now, these three components have an API in front of them, this control plane API, which is how you as a user configure them. Like the three separate components are invisible to you. You just interact with this API. And this API is declarative. It's like the Kubernetes API. It takes YAML files that declare the state of the world and the behavior as you'd like to see it. So that's a really nice property of this system. So we can begin. Our packet, which looks like a Nyan cat, because I think I've just dated myself there back to about 2005. This is a big room with some big PA. I should have had this slide like play the tune, but there you go. Nyan cat comes in, and the first place, so let's say the request we're looking at is coming from one of your actual end users on a laptop, on a mobile phone, somewhere on the internet. The first thing it has to do is cross ingress. So there is an ingress. This is standard ingress controller, Kubernetes ingress controller. Istio provides you with an ingress controller based on the Envoy proxy, right? And what this would replace the Nginx or the HA proxy ingress controller that you use. Now you can mix and match. You can keep your Nginx ingress controller and just use the sort of service to service sort of mesh parts of Istio. But Istio does provide its own ingress controller, and it's based on Envoy, which is a great proxy. And it's configured by the same configuration files that configure the rest of the service mesh. So if you go full Istio and use their ingress controller as well, then some configuration objects will affect the behavior not only of the proxies in the mesh, but also this bank of ingress. So it's a generally good idea, TM. Those envoys just do host and path-based routing like any other ingress system. They are controlled by the same control plane that controls the rest of Istio, which we're going to look at. And in the sake of time, I'm just going to skip this, and we're just going to kind of assume this works. So the first thing is you get an ingress controller. Say your user wants api.foo.com/v1/users, right? Routing happens at layer 7. We decide that that's served by service A. QED. I won't go into any of that anymore. So our packet is now on its way to service A. And it gets there, and what does it find? Well, there's no big reveal here. We know that there's an Envoy proxy alongside every service, right? This is kind of a logical diagram, so that gray box is not a host, it's like a service. And each of the blue boxes is a Kubernetes pod. So we know there's Envoy in this pod alongside service A, but what does that actually mean? Like, what is a pod, and how does this interception work? Well, it's early in the morning, so let's go back to some theory. What even is a container? Well, there's no such thing as a container, right? There's no first-class container construct in the Linux kernel. FreeBSD had jails, Solaris had zones. Plan 9 has these fully formed namespaces. Plan 9 is the best operating system, but we're on the wrong timeline. So we're using a student's copy of 4.4 BSD instead. And what it has is these namespaces, these 6 namespaces you can see here in these colored boxes. And they are a software isolation mechanism. So they isolate various software resources in the system. The first one is this gray box, the mount namespace. It's a lot like chroot, if anybody remembers that. It changes the process's view of the file system, right? So what we have here is a sort of Nginx container. It's just called Nginx, and it's got 2 processes in it, Nginx and then like a supervisor D to keep that running. These are standard Linux user space processes. They're just running in a slightly different context. They're a little bit isolated. So the mount namespace changes the view of the file system. If you think about that, that's entirely necessary because containers run from images. Right, so if Nginx here looks at user lib, it might see muzzle libc and an Alpine user space, right? Whereas the host might be glibc and Ubuntu user space because it's running from an Alpine-based image. So you need the mount namespace to change what it sees when it looks at / at the root of the file system. There's a few more. The UTS namespace isolates the host name, so this container can have a separate host name to the other containers and to the wider host. The PID namespace isolates the process table, process IDs. As you know, you like exec into a container, you do a PS, you can only see the processes in that container. The user namespace isolates user IDs. You can't see other users, and if you're user 1000 in this container, that is not the same user 1000 as in another container, so you can't read their files, you can't mmap their pages. The IPC namespace is a bit arcane. It stops, that barrier prevents System 5 IPC and SHM stuff. That's more just preventing a sort of attack vector these days. Nobody really uses that. And then there's the network namespace that isolates networking stuff. And we'll come on to that because obviously that's very important for our service mesh. So what is a Kubernetes pod? As we know, it's 1 or more, in this case 2, containers kind of strapped together. The Kubernetes documentation helpfully describes it as the atomic unit of deployment. And if you unpack that, it's the unit of stuff that you have to deploy together. You can't split these containers up. And the reason for that is each one of them isn't a full container. They share some of these namespaces. So necessarily they have to share the same kernel, right? Because namespaces are just a kernel thing, so they have to be on the same host. So they both have their own mount namespace. If you think about it, they need that because they're both running from a separate image, so they both need a separate view of the file system. They both have their own UTS namespace, so they can both have different host names, but they share the same PID namespace, so these processes can see each other and signal each other. They share the same user namespace, so user ID 1000 for one is the same as the other, and they can share pages. They can System 5 IPC each other if they want to, and also they're in the same network namespace, the same network context. So you think of the very sort of beginner description of a Kubernetes pod, it's one or more containers that share an IP, right? Share an IP address. So within this network namespace, there are several isolated networking things. There is, as the most obvious example, there is one interface, it's called ETH0, one IP address. So these processes all look for ETH0, they see an ETH0 with this IP, this 42, that would be different in a different pod. That's how you can tell it's a different interface in a different pod. They also have a loopback interface that they can use to talk to each other, and that is different to the loopback interface in every other pod, so the other pods can't listen in. Sockets, right, Unix domain sockets, open TCP streams, they're isolated in here as well, so is the root table, and so is the set of IP tables rules that are in play. So I could write an IP tables rule that says drop all traffic, right? Anything trying to come in or out of Nginx, supervisor D, fluent D gets dropped on the floor. But this doesn't take the whole host down because this doesn't leak out of this container, out of this network namespace into the wider host, and it doesn't affect any other containers or pods either. So for example, Nginx wants to offer a service, it binds to port 8080 TCP. Anything that hits address 42, port 8080 TCP gets to Nginx. FluentD can now not bind to 8080 because it's in the same network namespace, it's just going to get a port in use error. So that was an original example, I guess, of the sidecar pattern, right? It's the Unix philosophy. You take one tool that does one job and does it well, which is Nginx, and it knows nothing about, for example, log shipping, right? It just dumps the standard out. So you add a sidecar, you add a FluentD alongside that hoosts the logs up and knows where your ELK stack is and sends the logs off to there. That's the sidecar model. So we can replace that FluentD with something a little bit more interesting, say an Envoy proxy, and what that can do is offer network services like the FluentD offered logging services. And the way that works is because we have one set of IP tables rules within this network namespace that affect everything in this pod. So Envoy could write out a bunch of IP tables rules that say all traffic, well, that comes through me. So everything trying to get to that port 8080 across this little gap is sort of redirected into Envoy, and then Envoy actually spits it back out to loopback, and then from loopback there's more rules that get it there. That's how the interception works. That's how it's transparent to the application. You need no application code changes. This is one of the big advantages of a service mesh. You need no application service code changes to take advantage of this, and that's how that's plumbed together. So the way that's actually built is kind of interesting. So when Kubernetes starts a pod, when the kubelet starts a pod, there's code, your CRI plugin, so Containerd or Cryo or something, will make the system calls to start to build these namespaces. Liz Rice, the conference chair who works at Aqua, does an amazing talk on this. She kind of live codes 100 or 200 lines of Go that goes through all the system calls to set up these namespaces and basically make a container. I'd strongly recommend you find a video for that. But your CLI plugin starts to build these namespaces and it kind of gets this far. And then it's about to run the container you've asked for. Now, as I say, Istio is transparent. So as a user, you submit a pod spec to the Kube API server that's only got the one container in. You just want to run Nginx. So that's what you tell Kubernetes. Istio uses a mutating webhook admission controller. I couldn't say that when I was practicing. That changes that pod spec a bit. So it adds a couple of init containers, as we'll see, and then it also adds that Envoy container to the list of containers. So the first thing that happens is an init container. It's just the Alpine image, and it just uses the shell to run sysctl and turn core dumps on. And that persists, but for various reasons, that again is isolated by these namespaces, and that persists for the lifetime of this pod. So that tells you something maybe about the stability that the team is expecting. That's not actually true anymore. That went away in 1.0, but it's a fun slide to leave in, right? What does happen, and does still happen, is the next init container is this image called Istio/proxy init. It runs a very long shell script. I've done like a 3-hour version of this talk. If you want to know, if you can't get to sleep, go watch that, and I go through this in painful detail. What it does, very briefly, in a non-soporific way, is to set up these IP tables rules to do this interception, right? There's a couple of reasons it's an init container. One is that, again, it's a single thing. It does one job, and it does it well. The Envoy container doesn't have to know how to do this. And secondly, manipulating IP tables rules is a privileged operation. You can do it as root. What you actually need is cap net admin, that capability. So this init container runs with that capability. It does its thing, and then it goes away. It drops privileges. And then we're left with the list of containers, right? The one that we submitted in the pod spec, Nginx, and then the one that mutating webhook admission controller added, which is Istio proxy and has Envoy in it. And by that point, the IP tables rules are set up to do that interception. And Envoy, as it happens, binds to 15,001 on loopback, and that's how it plugs into the system. So I think we've covered how the packet kind of gets into the pod, what a pod is, and how it bounces through Envoy to service A. So it does that on the way in and on the way out. So next, routing. How does it know where to go? So service A has asked for service B, but like where is service B? Where should this packet be sent? How does it get there? So you can just let kubeproxy do it, right? You could throw this at the wire, at the Kubernetes network, and then kubeproxy would send it to one of the service B pods at random. You just get this round robin load balancing. As I say, I don't really have time to do the Istio pitch, but one of the massive advantages of Istio is because it's on the wire, because it sees all traffic and actually picks it up and parses it at all points. Because we have this Envoy sidecar everywhere, we can do much more intelligent routing. So rather than picking a service B pod at random like kubeproxy does, we know which one's is currently offering, like, empirically, a posteriori offering the lowest latency, which one has the lowest load. We can even know which one is closest to us, like in our host, in our zone. So Istio wants to take that decision. It doesn't just want to let kubeproxy do something. So how would it do that? Well, if I look in Kubernetes, if I ask the API server, what's going on? Well, what is this service? Okay, we're actually going for HTTP bin here, but what is this service? What I get is one IP, and this is the cluster IP. So this is no good. I fling a packet at this, and I end up on the kubeproxy path, and I just get one at random. So we can and we want to do better than that. Okay, so we know this service discovery information is also exposed over DNS. So let's look in DNS. Note, again, 1A record, cluster IP. This is cluster IP range. This is not a pod IP. This isn't really good enough. So I could guess, right? I could look at the pods and I could kind of grep, and I could be like, well, it's HTTP bin, so the pods probably have that kind of name. I got lucky here, but obviously this, as I'm sure you all know, isn't sufficient in the general case. Like everybody here knows what a Kubernetes service is. It's defined by that label selector, which can be arbitrarily complicated. It can pick pods out of more than one deployment or daemon set or whatever. So we got lucky here, but this isn't good enough either. Luckily, Kubernetes does give you a way to effectively get it to execute that label selector for you. So there's a resource type called endpoints. Now, you don't usually program endpoints in, but you can read them out. Every time you change a service, endpoint resources are made. So if I query the endpoints for HTTP bin, what I do get is pod addresses. This is pod IP range, and I get 3 pod addresses. So these are the pods. So now, this was just an example to show that in a Kubernetes environment, Istio can go and get hold of the actual workload endpoint addresses, and then obviously it can look at the information coming out of all the envoys in those, and it can make a much more intelligent decision about where to send this packet. Oh, right, yes, and if I dig into the endpoints objects in Kube, I get some useful stuff like, where it's running, the host and the zone and the region. So this is the first control plane component. This is a thing called pilot that sits up there on the control plane. And what it does is it sends this config to the Envoy proxies. It effectively sets up the routing, the path and host base routes to tell the envoys where to send these packets. And as I've kind of alluded to, one of the ways it does that is it goes and talks to all the different service discovery mechanisms that are in play. It goes and finds out where these endpoints are. So in the case of us just running in this Kubernetes cluster, Pilot doesn't even poll Kubernetes. Pilot establishes a watch on the endpoint objects in the Kubernetes API server. So every time a service or a pod comes and goes, it gets an update. And it kind of thinks about it and crunches it and compiles it and then sends root information to Envoy. If you've ever configured Nginx, right, you've got sort of server and location, a host and path-based. Envoy's data model is not entirely dissimilar to that. So it sends those routes down to the Envoy. As a quick aside, Envoy implements this. Envoy is API driven and implements this API that the Lyft team have kind of pushed out as an open standard, and they're calling it the data plane API. So this is meant to be an open spec for a comprehensive API for configuring proxies. The idea being that this is a nice open source ecosystem where you could swap Envoy the proxy out if you wanted with any other conformant proxy that talks to the data plane API. I believe today Nginx does that, but like don't quote me, and I think maybe another one does. So as I say, Pilot talks to the service discovery system. If we're only in Kubernetes, it's only going to talk to the Kubernetes API server, because every workload it's going to want to talk to, right? Every service is going to be a pod, and Kubernetes is going to be able to tell it where it is. If you're running outside of Kubernetes, then you would configure Pilot instead to maybe go talk to Zookeeper if you're running on VMs and they all register with Zookeeper. If you're in some hybrid mode, and you can do this easily, you can extend the mesh, it's called. So you can say, right, my service mesh covers everything in this Kubernetes cluster and also these VMs outside it where I've manually deployed an Envoy. You would discover the pods through the Kubernetes API server, and then again, your VMs might register themselves in console or Zookeeper or something. So Pilot can be configured to talk to more than one of these service discovery systems, and it'll pull all the data in, it'll crunch it, it'll deduplicate it, and it'll write one consistent set of root rules to all the envoys. So what can Pilot do? Because Pilot can effectively configure Envoy, its routing, and all of its other proxy-like features. I don't have time for a demo in this slot either. So what it can do is it can set up that ingress routing. It can tell the ingress controller to do all the things we want. And then it can use other Envoy features. So it can set up traffic mirroring, which is an Envoy feature, right? That's a piece of config you would give to Envoy to say when you're routing to this path, you're actually sending it to service A and to like service A prime at the same time. It can do traffic shifting, right? Classic A/B testing, of course it can, it's a proxy. It can do canary deployments. Now, if you think about canaries, they're really just a special case of traffic shifting. They're just a much smaller, you're just sending to two services, but you want to send a very small amount, like 1% or 1 request a second or something, to one of those endpoints. But Istio can do this because Envoy is on the wire. You couldn't do this with Kubernetes, right? If you've got 3 pods in a deployment, the best kind of traffic split you can do is 1/3, 2/3 with the way that kubeproxy works. Because we've got an Envoy on the wire, Pilot can tell it to literally just do, rand times 0.01 and just do a 1% thing. And then Envoy has other features because it's layer 7, right? It's an HTTP proxy. It knows what a bad HTTP response looks like. You get bytes back, but they're not just bytes to Envoy. It knows that that's an HTTP 500 as opposed to a 200. So it can do circuit breaking. It can do fault injection. It can do all that kind of stuff. And that's what Pilot configures it with. So can the packet come across the void yet? Can it get to service B? Well, maybe. There might be, it knows where service B is, it knows how to talk to it, whether to retry or whatever, but there might be some policy in place. It might be that there's an ACL, an access control list, denying service A from talking to service B. It might be that service B has a rate limit, and we don't want to talk to service B too often. Now, in isolation, in the dark, Pilot could configure Envoy to say, there's a rate limit on service B. If you're ever talking to service B, 1,000 QPS max, please. In this case, we've got 3 pods, so the service Bs would get 3,000 QPS, right? But let's say we ship a new service A that's just, the code's a bit inefficient, and the autoscaler suddenly means there's 10 pods. Well, now you've got 10,000 QPS coming across to service B as a side effect of that. So that kind of, you can't make these decisions in the dark. That kind of mechanism wouldn't be good enough, and you need global coordination, right? Say all the service Bs, we know every time they get a request, they talk to a database. That database has a certain size, so however many service Bs there are, between them, they can only take 1,000 QPS. That kind of globally coordinated, global rate limit needs global coordination. And that's where the second component comes in, and that's a thing called mixer. A mixer is kind of on the path, if you want. It's kind of on the wire. Every time Envoy gets a request, it calls to mixer and it says, what should I do with this? Is it okay to send it? Have we popped the rate limit for this minute, this second? Does the policy allow it? So yeah, things like ACLs, things like RBAC, service to service RBAC, if that changes, you don't want to wait for Pilot to recompute it and push it out. You want to make that decision like right now. So those requests go to Mixer as well. And also it doesn't have to be necessarily a thing that's within Istio. So your policy decision of can service A talk to service B might actually be farmed out to an external policy agent, right? So in which case, all of these envoys need, rather than them knowing where that policy agent is and knowing how to talk to it and have credentials for it, they just talk to Mixer. And I think, yeah, this next diagram shows it a bit better. Mixer will just talk to those external systems. So as I say, every request that comes into an Envoy gets sent, it gets parsed, the headers, the metadata gets sent off to Mixer, and then Mixer can do various online things. Okay, so Pilot does configuration that kind of changes on human time. New pods come and go maybe every few seconds, but for things that are like per request, that's Mixer. So the metadata gets sent up to Mixer, and it does two broad categories of things. The first is to report. So it'll write logs about all the packets, say into Elasticsearch. It'll create metrics about all of these requests. But because you've got an Envoy on both sides, you know what the real latency is, you know what the actual bandwidth, you know what the actual sort of byte rates are. So all of that can be made into metrics, and that can be reported up to, for example, a Prometheus system. And again, rather than all the envoys having to know where each of those systems is and have credentials for them, they all just send it to Mixer. Mixer aggregates it, and Mixer sends it off. When you install Istio out of the box, it'll ship you a Prometheus and an Elasticsearch, just as an example, and it'll configure itself to just put your metrics into those systems. But you can configure Mixer to send metrics to Stackdriver or to CloudWatch or to any like Sysdig or to any other system that you're using. And you only have to do it once, right? It's only Mixer that has to know how to do that. The other side of what it does is the check side of things, which is where it says, well, we're trying to make this request, is it allowed? And that's where it would look at, say, a rate limit, which it'll just count up in memory for you for some service-to-service RBAC rules for ACLs. And again, these are internal things. You write Istio config files that describe those RBAC rules, but you can configure Mixer to say, every time you get a packet, I want you to go talk to my LDAP system, right, and see if the owner of service A is allowed to talk to the owner of service B. So this all comes through Mixer. This makes a lot of people squint, right? Because this looks like a single performance bottleneck, and it looks like a single point of failure. So why is the architecture like this? Well, I mean, it is a single point of failure in that it's a single point that can fail, but the whole system is really designed to be resilient to that. And if anything, Mixer makes reliability better. And the key to that is caching. So on the reporting side of things, we parse the headers, we send them up to Mixer, Mixer sends them on. That's asynchronous. So if Mixer is down or can't be reached, that doesn't block the main Envoy thread. Envoy continues to forward packets. That's asynchronous, that's batched up. Some aggregation can also happen client side, so you said less stuff across the wire. So that's absolutely kept out of the main thread, out of the way, and if it has to fail, then if that buffer gets full, it will fail, and Envoy will continue to honor the routes that it's been given by Pilot. As for the checks, the key there is caching. So Envoy has what's called a filter. It's got a plugin mechanism. So there's an Envoy plugin that talks to Mixer and gets these answers, these yes or no check answers. And that client for Mixer is what's called FAT, right? It's a big lump of code. It's got a lot of logic in it, and most of that is around caching. So Envoy parses say an HTTP packet, sends all of the headers up to Mixer, and says, right, a user wants to send, service A wants to talk to service B, and it's accepting encoding JSON, and it wants gzip compression, and the content length is like 72. Mixer goes and looks at all of its rules and says, that's not allowed. You can't do that. That request can't go ahead. It's a no from me. But when Mixer sends that reply, it sends the cache key with it. So it says, right, so I looked at all of the headers you sent me, but the reason it's a no is just your source and your destination, right? Service A is not allowed to talk to service B at all. So I want you to cache this no, and I want you to cache it under a key of source service A, destination service B. So if another request comes in from A to B, it's automatically a no. The fact that it's a different language, it wants bzip encoding, right, and it's XML rather than JSON, doesn't matter. the cache key for this is just the source and destination. So those minimal cache keys are sent back by Mixer with its replies, so that this cache can be as wide-ranging and as optimal as possible. Mixer also gives 2 TTLs for that answer, so it gives a cache expiry in terms of wall clock time, and it gives a cache expiry in terms of the number of requests. So it can say it's a no, and it's valid for a second or 300 packets, whichever comes first. So that's all about making sure that if Mixer goes down or is slow to respond, that you hit your cache absolutely as much as possible, but still you have this safety. So if something comes into Envoy and it's not in the cache, it's a new kind of request pattern that we haven't seen before, Mixer will go and be asked, and you've got an online instant policy check, and you've got sort of global rate limit enforcement. And that's kind of the reason that in this picture I took it out of its little hole up here and I moved it down. It's technically control plane, but I would say it's it's closer to the data plane. It's more like the sort of slow path of the data plane, because it is on that request flow. But a lot of steps, as I say, have been taken to mitigate any adverse effects of that. So what can Mixer do? Well, as I say, 2 broad things: report and check. The reporting is your 3 pillars of logs, tracing, and metric, but there are lots of pluggable backends it can talk to. And your checking is checking access control lists based on RBAC policy and rate limits, and a few other things. So can we finally send the packet across? Maybe not, because this lady here is called Eve, and she wants to drop in on our conversation, right? So we said that the services, the business logic becomes super simple. These services, they don't bother with retries or timeouts, they don't throw circuit breakers, and they also only talk HTTP. So no longer do I have to make a TLS certificate, bundle it with my application, worry about rotation, which nobody ever does, right? These things are always just really long-lived. Envoy can do all of that for me. It can, and it should, and it does. So what the envoys will do is they will put that communication in a TLS tunnel on the wire, so that the communication is encrypted and Eve can't listen in. That needs certificates, and that brings us on to the 3rd and final control plane component, which is Citadel, which is basically a certificate management system that generates and rotates those certificates and configures them into the envoys. This is mutual TLS, so if you think about like the way the web works, the server would offer up a certificate, the client would check it against its CA bundles that are installed, but the server has no real way of validating the client. Like the client doesn't, your web browser doesn't present a certificate, which is why websites have to ask you to log in, right? They have to move that up to an application layer because you have to prove who you are. In this case, Citadel gives certificates, TLS certificates, to both sides. So both envoys have a cert, and they can do mutual TLS, mutual verification of each other. And then based on that, I've got a certificate with a CN in, an identity that says I'm service A. That's what the sort of service-to-service RBAC authorization rules are based on. The whole thing about identity and authentication and working out who these services are and if they really are who they say they are and whether they should get a certificate with a certain name is a whole nother talk. It's the spec called the Spiffy spec. It's quite interesting. So I would say, finally, we are done. The packet has reached the end. We've seen it's come in. It's been routed by ingress, provided by an Envoy proxy, configured by the Istio control plane. It's bounced in and out of Envoy with transparent injection of the proxy, transparent interception of the traffic. It's come across an NTLS tunnel. It's obeyed all the policy. And again, it's done the same dance. It's bounced in and out of Envoy on the other side. A couple more things to say. I think I'm actually doing just about right on time. Another couple of things to say is that, of course, the control plane has an API, which are used to configure these components, but they need somewhere to store that config, and they need to be able to watch the configure updates, all that kind of stuff. So what you really need is a sort of database and an API server to front it. When we're in Kubernetes, we just hijack the Kubernetes one. So when you install Istio, it actually writes a bunch of CRDs into the Kubernetes API server to say, hey, you're expecting some more configuration documents with the following schemata. And then what Istio CTL does, which is the equivalent of kubectl, your user sends the Istio config just up to the Kubernetes API server. They're Istio format resources, but Kube is expecting them because the CRDs have been configured, right? And it uses the Kube etcd to store it. If you are running outside of Kubernetes, then you have to run this infrastructure yourself. The one final feature that it has is egress control. Kubernetes obviously doesn't do this for you. There's no real concept of an egress controller in Kubernetes. Normally, there's no egress object. Istio does do it. So again, we can apply the same kind of network services to egress. Let's say service B ultimately wants to go and get a picture of a kitty off the internet. We can have this bank of egress proxies, retry connections to kitty.com in case it's a little bit unreliable, apply a rate limit, so everything in the cluster is only making 10 requests a second to this website on the internet, so they don't think we're DOSing them. You can do path rewrites, host rewrites, all the features are offered by the egress. Or you could say, well, my cluster is an internal service. I have my data and my logic are inside this cluster. I'm serving my users who are using my iPhone app. Nothing really should be reaching out to the internet. If anything tries to connect out, I've probably been owned. So I actually want to deny, it's quite a common configuration, is I want to deny all connections to the internet. And if anything tries it, of course, these envoys talk to Mixer too, so they will report that up into Mixer, it'll appear in your logs, and you can just set up a Prometheus alert that says, something's trying to talk to the internet. Like, is it just doing a shitty self-update, or has it been owned? So we saw how that packet comes in, traverses the Istio system, leaning heavily on the Envoy proxy, and this was in the context of Kubernetes, which is hopefully what you're using. We saw how the control plane does that and how the various components do what they do, and the split between pilots kind of ahead of time, human time, static configuration, and Mixers online policy enforcement. And hopefully that's a useful mental model for what's going on and what a virtual service does. You can imagine hopefully which one that is and what a destination rule does. And yeah, please go in, take the lid off and have a look around Istio. So thank you very much for your time.